suddenly I get a text about my data is gone. So this session we're going to get into state machines, we're going to talk about decision making, and we're going to solve some problems in a really different way than I think you guys have probably seen before. Definitely a different way than I had thought of when I was in school, but it's actually a really pretty cool way. So what we're going to talk about is Stateflow. That's the MATLAB stuff. Before we get into the agenda, as I dug into what we needed to do to be able to hit something, there's just no way we can do all the software in 2 hours. So we're going to do one more software session next time, another couple hours. And we'll talk about why. There's some big stuff that we have to do, and there just isn't enough time to do it. So we'll get half of it done today and the other half done next week. And then what we'll do is we'll combine the SolidWorks parts and assemblies week, and that way we can still get done in 12. You guys getting cozy there? Don't worry about it. Okay. Okay. Everything else still as it was. Okay, so today's agenda is we're going to talk about finite state machines. Who knows what a finite state machine is? If I sound, yeah, okay. Or just state machine. And then we'll talk about how you represent them more easily in Simulink. It's called Stateflow. is the software package that helps us, and it actually makes some really wildly cool abstractions for us to express stateful systems. And I'll show you how we can do the whole bouncing ball example in like I think it's 8 lines of code with Stateflow, which is pretty cool when you think about all that. We spent 4 hours at least on the bouncing ball example. We can do that in like 8 lines in Stateflow. So that's pretty cool. We're also going to talk just about subsystems so that we can make life easier on ourselves for abstractions, that kind of thing. And then we're going to get some project work done. We're going to spend most of the couple hours doing that project work. There's 4 things that we need to do to finish the software side of stuff for targeting and being able to hit something. And that's prediction, time of flight and elevation, lead time, and fire control. And we're going to do time of flight and elevation and lead time today. So that's so let me pause there for a second and refer. I almost forgot to tell you why I showed you the Humphrey October thing. So remember how they were talking about, torpedoes coming in, this is such and such a range, such and such a bearing. And so one of the reasons we didn't do our project wasn't firing from a submarine, because that makes the problem 3D instead of 2D for one, and then takes so much longer for the torpedo to get there, makes it even harder for another. But what I wanted to point out was, did you see when Sean Connery asked Sam Neill, Vasily, do you have a solution plotted yet? Right before he got shot. And he said, yeah, well, it's a little rough, but basically it was rough, it wasn't perfect. The reason I wanted to point that out is, even in the next scene, I didn't want to keep going, but in the next scene, the guy that was firing the torpedoes on them was saying, come on, hurry up, set the safety ranges to 0 now. I mean, basically, they're trying to rearrange and modify the programming of their torpedoes, and it's just not perfect. It's not immediate. It's not, snap, snap. And we'll get to see a little bit with our particular solution why it isn't just immediate. Like, okay, here's the solution. Press a button, here you go. Because we're going to use a numerical solver inside our solution to converge on a solution, so it takes some time to get there. And that's why Sam Neill, Vasily, was saying it's a little rough. So basically, we're going to have the same kind of thing. Like, it will get progressively better the more time we give it, which is kind of cool. You have a question?
That's actually not related to MATLAB. It's about some read stuff, so probably should.
Okay. Well, if we can answer it in 30 seconds, sure, go for it.
No, I was just wondering what kind of explosives to use in the warheads for torpedoes, because I'm assuming since high pressure, could it take too much of an explosion to make a hole? You just need to make somewhat of a hole in the submarine to make it go away, right? To make it sink. So I was wondering,
I
how
don't,
much explosives like what and like.
I don't know exactly, but
I just want to get it a lot smaller. I mean, you carry more and go faster if you use a higher explosive round.
yeah, I'm not sure, but it's not always. I mean, it seems like you wouldn't need to make much, but then again,
That must be the torpedoes seem so big, you know. The torpedoes seem like very large, and I was wondering like if they have to be that large to sink another submarine.
Oh, yeah. Well, I know that a lot of subs have survived more than one torpedo hit, and so maybe that's part of it. They want to have enough payload so they really put a dent in it. And also, some torpedoes aren't. I mean, you might want to shoot at a ship with it, and
That's true. Yeah.
you know, like the battleship that we're mimicking had like 18-inch plate armor. Like that's how thick you. That's just the steel. You know.
That makes sense. It's probably for the ships.
Yeah. So yeah, but I would imagine it's easier to penetrate the hull of a submarine. But then again, they have to go 1,800 feet down. And there's a lot of pressure, so I'm not sure. Okay, interesting question, but don't know the answer. Okay, so first thing first, let's talk about finite state machines. So finite state machine is a mathematical model of computation, and I think this is a nice, easy one to start with, the turnstile. So if you look at this lower down here part, these bubbles, these circles, are the states that the machine can be in. And when I say machine, I'm not talking about this machine. I'm talking about this conceptual diagram. Okay, so the machine takes particular states, and so it has a locked state and an unlocked state. And then it transitions between those states. So you're in the lock state, and this little dot with a line, that's the default transition, so that's where you start. You can think about it like a computer when it boots up into something first, and that's what the default transition is about. And then there's transitions, so if you're in the lock state and you put a coin in, then the turnstile goes into the unlocked state, and it stays there until, and if you put another coin in, it stays in the unlocked state, right? But as soon as you push through it once, it becomes locked again. And if you try to push through it again, it stays locked. So it's a really compact, efficient way, and people have been using state transition charts like this for a long time. But the really cool thing about Stateflow is that's how you create state machines. You just draw a state chart. And so you can make extremely complex logic and update it and understand it a lot more intuitively as compared to writing code or making a Simulink model or something else. And it can interact with all that stuff. So, yeah, there's always an initial state. They're directed arrows. So we already said all that stuff.
I don't know if you're going to talk about this later, but how do you account in a state machine for if you're accumulating some value? Like, let's say that turnstile has some counter where that's the number of coins that are in, so that's the number of passes that will allow through before it locks up again.
Right. We will get to that. There's basically in each state there's action script that is what happens in that state, and you can write MATLAB code in there, and that can handle stuff like you're talking about.
Okay, because in Dr. Ma's class, he ended up having us represent each state as in this is how much money you have. Like here's where we have 1 coin. This is the state where we have 2 coins. This is the state where we have 3 coins. Then you end up having a certain number of states to represent just simply integer value.
Yeah, yeah. And it feels like that's kind of a waste of states, right?
Yeah.
Yeah, and so you could do it that way, or you could, like you said, add it up in the state you're in, and
Okay.
yeah. So they're different. They're just different ways of talking about state, right? And some are more intuitive than others.
And that was what I was curious about. I'm sure you know the way that makes more sense or is more compact and simple, where you can use a state machine and then have some, I don't know how it works, but value counter or whatever that is accounted for in that simple state.
Right. Yeah, I think towards the middle of the thing, you'll probably be like, I know how I do that. So, okay. So context. It's always nice to know where you are, kind of have that you are here map. And so combinational theory is like if you could maintain no state at all, like a pure functional space, like the sign of 2 is always 2, no matter what the last thing you asked sign to compute is, right? That's a combinational type of logic. We're kind of going one out from that, and we're talking about a finite state type of logic. And we can keep going out, but I'll just kind of direct your eyes to the bottom of the diagram there. It says Turing machine contains all of those pieces. Do you guys know who Alan Turing is? Or
Yeah, he's one of the computer science pioneers.
Yeah. Have you seen the movie? What's that?
I know
They said they made the movie.
Yeah, it was a great movie.
On Netflix. I haven't seen it yet.
Okay, yeah. I thought it wouldn't be very good at first, and I watched it. I was like, wow, that was a great movie. It's called, what's it called?
Imitation Game.
Imitation Game. Yeah, super good.
I heard the Apple logo was inspired by him.
I have no idea.
Committed suicide by eating.
Yeah, cyanide based apple.
That's how you commit suicide.
Is that really the apple logo has a biting on it?
That's what I've been.
Seems like a really morbid reason
Yeah.
to make a logo for your company.
Yeah.
Let's name it after the guy that killed himself.
His name, yeah.
Yeah. But anyway, so we've actually already done state machines, just not this way. And you'll see when I show you the state diagram for the bouncing ball, you're going to be like, we spent so much time. But it's we were learning something else at the time. So that's it for the theory. So let's talk about how we actually do this. Okay. So get in here. While this is loading up, basically I'm just pointing out where this stuff is. For the longest time, I was telling you guys that I had purchased this stuff and spent a lot of money on it. I never used Stateflow because it looked like there wasn't much to it. You click on the Stateflow library and there's 4 things in there. There's a chart, state transition table, and a truth table, and I thought, what am I going to do with that? It just didn't look. But actually, it's one of those, like, the simplicity is the beauty of it kind of things. So let's hop into it now. Okay. So day 6B. All right. So I'm going to start a new model up here. I think the mistake, or I'm trying to get better at presenting so you guys stay more engaged and pick this stuff up faster. So I'm going to go directly into sort of a sub-problem so we can talk about something instead of before we get into all the details of the conceptually the way it works. So this is, we're going to talk about our reloading state machine, right? How does that work? So you have this chart here, and we'll show how we can, inside the chart, create a state machine, and then push inputs and outputs, all that kind of stuff. Alrighty, so there you are. Okay, so we go to Stateflow and drag a chart on there. As soon as it loads. Okay, so now to edit the chart, we double click on it, and it's like we've kind of gone into another space, right? You can tell because it's all yellow background. And on the left are all the different elements that we need to create state charts. So if we click here on state and drop it in, it comes with a default transition because it's the first state we made. So I'll call this one init. And let's actually, we're just going to copy off of the what we have here. Let's talk about it first, though. So we're trying to model, I mean, this whole thing is about modeling, right? So what we're trying to model is what happens for the reload, and, you know, it's time to reload, it's not time to reload. That's a very stateful kind of thing. Is the gun loaded or not? Okay, so what we're modeling here on the right is when you first turn on, when we first start the simulation, it goes into this init state, right? Up in the upper right. And there's the default transition. And then it unconditionally goes to this junction. And it says if preloaded is equal to 1, then it's ready to fire. And if preloaded is equal to 0, then load the cannon. Okay, so the idea there is if we all load the cannon, went to lunch, came back, and then turn the simulation back on or turn the computers back on, that's kind of what we're talking about there. Is it already loaded? If we're not loaded, then load the cannon, and after 4 seconds, let's just say we have a really fast crew, after 4 seconds, it's loaded. So the condition for this transition is a certain amount of time. And I'm going to point out why this is called SEX and not SEC, S-E-C. SEC refers to simulation time, so that would never reload. We'll talk more about why that wouldn't work. SEX is this incoming signal, which is a clock. So we're talking about ticks of a clock, and you'll see what I mean in just a little bit. Okay, so let's draw this thing. Where'd you go? Okay, so we have init. Okay, now we use this keyword entry, and that means when we enter the state, the first time step we get, what we want to do there. And so we're going to tell the output that its value is 0, because we don't want to tell the fire control that we're ready to fire too fast. Okay? Now we need a junction block, one of these guys. One conditionally go there. And then from that, on this side, we'll make a state called load cannon. And on entry, ready equals 0. Make another state called ready to fire. And on entry, ready is equal to 1. Okay. So a couple of things here. I'm just hovering by the edge, and I'm drawing lines and arrows.
So is EN colon the same as entry colon?
Yeah, it's the same. So there's entry, during, and exit, and we'll talk more about what those are in a little bit. It just has to do with when you enter a state, sometimes you want to do something in the very beginning, and then something during the whole time you're in it, and then something when you exit. And so there's three, they're kind of like substates of the state model. And it just makes it so that you don't have to have so many more states. It's like you were talking about. Like you'd rather just keep track of a little spinner inside one state of how much change you put into the vending machine. Okay. So this one we said preloaded equals 1. Okay, now I just typed it as is, and I'm going to click over here, and I just want you to point out that it put brackets around this. That's because the brackets are conditions of why you transition. You can also put commands in the transition, which we'll see in a little bit. And this one is going to be preloaded equals 0. Oops. Equals 0. Okay. And the 1s and the 2s are the order of the execution. So it's going to first check. See, this has a 1 and this has a 2. It's going to first check to see, am I preloaded? And if it is not, or if it is rather, it's going to go in here. And then it's going to check this one, the second execution condition, or transition. It's going to say, am I preloaded? And that's equal to 1, so I'm going to go ready to fire. Okay. Now, I'll put in, okay, so before I add more here, I want to show you something else. I'll save this as, call it reload 1. Have we talked about Control D? I don't think we have yet. Control D is update diagram. So you're basically saying rebuild yourself, check your consistency, but don't actually run the simulation inside Simulink. So I'll hold down Control, hit D, and it's going through and compiling. Okay, now we implicitly talked about preloaded and we talked about ready, but we didn't say what they were. And so the symbol wizard comes up and it says, hey, I have some unresolved symbols here. Help me out. This is what I think they are based on the way you used them. And so you can check the ones that you actually want to make. Sometimes you misspelled something and they come up, 3 different spellings and you don't want to make all those. And that's right. We want preloaded to be an input and we want ready to be an output. So I'm going to say OK. Now, as soon as I do that, if I hit escape or click back 1 up on the tree, you can see that I have a preloaded input and a ready output. So we're starting to kind of blur the lines between a block diagram model and a script code type of model, because we have ports coming in and we have these blocks, but we're not pushing data along the transitions along these arrows like we would be with blocks. So it feels a little different, Okay, so let's finish creating this thing. Okay, we'll say after 4 secs. I'm going to do Control D again, and it's going to come up and say, that looks like an event. It's not an input. It's a little bit different. There's events, there's messages, and there's data with state charts. And this is an event. And so an event is kind of a true or false thing that happened. And, like you were talking about before, Tony, you could think about events as coins. Like a dime was dropped in, that event goes true. And when you say after 4 secs, you're saying after 4 events of the sex type. Could have picked a better word, but that's what it is. So anyway, it's inferring, I think you mean this to be an event, and we do. So we'll say OK. And if we save that and hit escape to go out, you can see we have a little, let me zoom in here a little bit so you can see it. We have a little rising edge event input. Okay, so let's finish this guy off. So the other thing we need to do is transition back from ready to fire back to load cannon when fire 1 equals 1. And that's good. So you were asking, Tony, about how do you actually do stuff inside the state. That's what all this stuff is. Ready equals 1. You can do if then else. You can do all kinds of stuff. You can actually, it's kind of cool. It's like a little microcosm. You can actually put Simulink functions and MATLAB functions inside a state chart and then call them, which is pretty wild, actually. Okay, so we'll save that. I'm going to update the chart, and it's going to tell me, oh, fire 1 looks like an input. Yes, it is. Okay. So I'll hit escape. Now we have preloaded and fire 1 as inputs and ready as an output. So let's feed this some data so we can test it. So we'll put a couple constants on here. Oops. Let's pretend that we are not preloaded. We didn't go to lunch with the cannon loaded. And but we do want to fire as soon as we're ready. And we'll put a scope here so we can watch the ready signal in time. But we really want kind of a clock signal, but there isn't like a digital clock, you know what I mean, like a square wave type of signal. So it's ticking by at a certain amount of time for this application. We could use anything we want. We could make this a conditional thing, like if this condition's true, this event happens. But for this, we want to make it like a clock. So the way we do that is with the counter block, the limited counter block. So I'm going to drop that in here. And so all we have to do is make the upper limit 1. So it goes 0 to 1 and then resets. 0 to 1, 0 to 1. So, and then we'll set the sample time to be, how about 1/10 of a second? Okay. Now, the sample time of this, I'm right-clicking on it, and I'm going to go to block parameters, and where are you at? Should be in block parameters. Let's treat it as an atomic. Okay. All right, so let's run this. It should execute as at 1/10 because it should be being driven by this. These should be infinite sample time. Okay. So let's watch it and just see if this does what we think it's supposed to do. So maybe we should start there. What do we think this should do? It should start, go into init, ready should go down. Preloaded was 0, so it should go to load cannon. After 4 ticks of the clock, so our ticks, our secs are 1/10 of a second, so it should take 4/10 of a second to get from here to here. And ready to fire should become 1, and then it's a transition back and go 0 again. So I'll hit run. I'm probably going to regret having this go for 10 seconds, but that's okay. It'll be done quick. Okay. So let's see if this makes sense. We have 1/10 of a second sample time is 1/10, right? We're driving this thing. 1/10 of a second. We'll talk more about what I'm about to do right here, but I need to hop into the Model Explorer and double check why. Yeah. Okay, it's inherited. Okay, I just need to make sure. All right, and I'm going to change the time of this guy to 2 seconds instead of 10, so we can not run so long and think about it a little bit more. So why did it take till 1.1 seconds before it went up? So I'm going to set a breakpoint on this when transition is valid, and then we'll step through it. Because this really helps. This is kind of the nuts and bolts of making state charts. You need to know how something continues in execution. So I'm going to hit start, and it's going to hit the first breakpoint first thing, right? And so at time 0, this should be true, and we shall see here. It's compiling it. Sorry, 0.1. Okay, so we take one step through, and we're in it's still 0.1. The transition doesn't take any time. Then the next step is the time we spend in it. The next step, we're in load cannon. 1, so that's 1 sec. 2, 3, 4, 5, 6, 7, 8. Well, that's not the way it's supposed to work. Force secs should be driven. Oh, it took twice as long because I almost forgot. Sorry. This is only looking at the rising edge of the clock. So it's going half the speed of the clock. So if we look at this, see we're only looking at this rising edge. So let's fix that real quick. And we'll talk more about this in just a moment, but we can go into this thing called the Model Explorer and really dig down deep into the properties of what we're doing. And so if we want to talk about the sex event, if we want to talk about that, we have to stop this. Okay. And it says triggers on rising, following either or a function call. I'll just change it to either. Okay. All right. Finally. So we would expect, and go back in here, we would expect it to be somewhere around 6 or 7 times 10th of a second for this stuff to happen. So, come on.
Where was the trigger? It's in the Model Explorer, the charts.
Yeah, so if you look at the Model Explorer, and then under chart, you can click on the sex event over on the right-hand side. When you're not running, you can change the trigger.
Okay, so either?
Yeah, either.
Okay.
And so now it's actually getting there at 0.6 seconds, which makes sense because we had to get through all this stuff and spend 4 sex events until we could transition. And then, since we unconditionally go back, we go from 0.6, and then at 0.7, we're back into load cannon, and it'll take us 4 of those, and then we fire again, or we're ready to fire again, and we fire. Okay. So that's, just pause here for a second. We're going to use this all evening, so if you have some questions about it, ask me while we're on a simple one, and because we're going to launch into some more complex ones.
So every time it makes a move, that takes 1 tick.
Yeah, if that's, remember we were talking about multi-rate systems. We were talking about how something might be happening at a different rate as compared to something else. You can change because this is a piece of software that what this particular thing is emulating, right? So we can tell it to run faster than the events are happening. And then it's just on us to synchronize them. The way we had it, I'll go back to Model Explorer here and show you this. When I click just on chart, it has update method of inherited. So if a data input changes or an event happens, then the state chart is triggered to execute and identify what's going on. So that could actually happen in a non-fixed rate way if we wanted it to. Because we can change this to be discrete, and we can actually make it continuous too. And that's how we'll do the bouncing ball here in a little bit. So, yeah, that makes sense?
Yes.
Okay. So, discrete time intervals of a state machine. The very first, so if these little orange tick marks are the discrete time steps, the very first one that's inside state 1, that's the entry. That's the time the entry is true. So whatever is kind of filed under do this during entry, that's when it will happen. Then there's the during state, which is everything else that's part of the state. And then there's the exit, which is right after the state is no longer. So it's kind of weird, and I had to play with this for a while to wrap my head around it. the exit state isn't even in, the exit state of the state takes place after you're out of the state. And you kind of think about it, I think about it like house cleaning, you know, and after you've left, then house cleaning comes and does whatever. Then as part of this, just so you're oriented, these are the transitions. So the transition happens right on these boundaries, and then you're in state 2. So this little interval right here is the exit of state 1, and it's also the entry of state 2. So if you did two things that interfered, like don't agree, and maybe the exit of state 1 said ready is equal to 1, and then the entry of state 2 said ready is equal to 0, it's going to go with whatever state 2 said to do, because that's kind of the new boss, if you could say it that way. So does that make sense? Yeah.
So, that part does, yes.
Okay.
For during, does that get executed for every tick in this case? Is that like a set of commands that gets executed for every tick, or is there some other condition that the during?
It's not for entry, just the stuff after entry.
So let's say you enter it and then some other command is satisfied such that it moves to a different state. Then during never gets executed.
Yes.
But let's say it goes to enter and then it, for whatever reason, it stays there for a total of 3 ticks. That means during is going to execute twice.
Exactly.
Okay.
You got it.
Thank you.
Okay, so this is discrete time. This is a discrete time, and this is, 99% of the state machines I've made are discrete time type of state machines. But I think this is pretty cool. They don't have to be. They can be continuous time. So what that does to the you can call them substates, or the entry and during and exit, is those entry and during shrink to not having any time duration. So now the during, if you think about what continuous time and discrete time mean, they mean that time steps become infinitesimally small. So you can think of, it's almost like, in calculus, and talking about how we're going to take an infinite number of intervals and then they all shrink to basically 0. That idea is the same here, where this is now the exit of state 1 and the entry of state 2. That's no longer an interval, it's a point in time. And the during spans the whole part now. So, and we talked about the fact that these are finite state machines. Like, it's in the name, it's got to be finite, but that doesn't mean you can't have continuous variables within a finite state machine. And you'll see what I mean in just a second, because it's a different way of thinking. A couple things to note. I'm not going to go through all these things. These are kind of for your info. You can pause it if you're reviewing this later, or look at it. Just a couple things I do want to point out. Variables are implicitly persistent. Inside a state chart, you don't have to say this is a persistent variable. Everything's persistent. Yeah.
You said pause it if you want to do this later. Are these videos or?
Yeah. YouTube.
Yeah. Okay.
I can give you the link.
Okay, I just want to hear something here, so I was.
Oh, okay. Yeah, I'll put you on the mailing list if you like. But yeah, that way, because sometimes I need to go really fast and I feel bad, but you can always go look at it again and catch up with whatever you missed. Another quick note I wanted to make, there's a lot written on this slide. I just want to point out a couple things. The bolded part here on the right-hand side, you have to use Model Explorer to edit certain aspects. Like, you can't, at least not that I'm aware of, you can't go and explicitly say this is a rising and falling edge type of event that I'm talking. You have to do that inside the Model Explorer. So what we traded in our interface to make the model was a whole bunch of things happen implicitly, and then when we want to do some explicit tinkering, then we use another tool to do that. So it's just a trade-off of interface. I think it's a pretty brilliant one, yeah.
Question about continuous
Yeah.
time. I'm a little confused as that, because the discrete time would make sense when and how many times something executes or a block executes. Right. How exactly does that work in continuous? Or how is it treated?
Why don't we we'll do the example with bouncing ball. I think you'll see what it's like. Nothing like an example.
Agreed.
So we already kind of went into the Model Explorer. That's where it is, just to the right of settings. And you can browse not only the model you're in, but you can also browse, like, there's other models, and you can select different things. And you can change parameters in your model, kind of explore all the models you have open. It's really powerful. You can search for things, like, I can't remember where that block is. I know I named it delay, and it'll just go and find all the delays for you, so really powerful. Okay, so I'm going to pause here. This is the bouncing ball as a state machine. And stop and think about what your definition of state is in your head, because this has one state. And, you know, most of the time when I think about a state machine, I'm thinking at least two. Why on earth would you have a state machine otherwise? This only has one. So let me kind of walk you through why. So our default transition has two initialization conditions. So remember how the conditions that we transition on are in square braces, but the commands we want to execute are surrounded by curly braces. So this sets p equal to 16 and v equal to 12. And p is position and v is velocity. Okay? And so the only state we have is the falling state. So this has gravity. And we could make it more complex, but we said during, because of the fact that in a continuous regime, like a solve regime, there really isn't any entry or exit unless you're only talking about a particular point in time. So during the whole time that this is true, it's actually doing something with v and p, and then there's an output called p out to push our value of p to the outside world. Okay, so what's p dot and v dot? If you remember, I don't know if everyone here's had calculus, but in calculus, the first derivative of a variable, in other words, how it has changed in time, is called one of the annotations is the variable with a dot over it. And the second derivative is x double dot, so on. So implicitly, p dot and v dot are the time derivatives of p and v. So whatever variable you have, if you append the underscore and dot after it, that's what that's talking about. So if you think about this, this is the opposite way of talking about what we did before. And I look at the bottom, second to last bullet, it says, previously we defined the bouncing ball as accumulating stuff, like time integration style. So P equals P plus V times TS, right? And we've beat that with a stick really good. Our new position equals our old position plus how fast you're going plus how big a time step we were going that fast. So if you think about that and kind of rearrange this equation a little bit, sort of intuitively, and you can say this way is just saying that velocity is equal to the time derivative, or P over TS, the change in position over time. So I don't want to get into trying to teach fundamental theorem of calculus. That's what this is. It's kind of beyond the scope of what we're talking about. But if you're not sure about this part, we can talk about it later, like afterwards, or hop online and check out the fundamental theorem of calculus. It's pretty cool. Integration and the derivative are inverses of each other. So that's what that's about. And now this transition is, the condition is when you get below zero, right? When P is less than zero. But what you do there is set the position of zero and reverse your velocity, so it'll bounce. And so it's resetting things and then changing your velocity. And so what this does is it actually determines, remember how we were talking about zero crossing and how previously we have to account for the fact that when we get to the wall, we're probably going to go past it, so we had to compensate back for the fact that we went past it. Well, this, because it's a continuous state, the Simulink solver actually figures out when it's going to hit. It puts the solve point right there, and it reverses it, and it's pretty cool. So I'll make this real quick so that you can see it. All right, chart, state, falling during P dot equals V, V dot equals minus 9.81, P out equals P.
Does it matter if you put V dot in that at that point, or even in the top at the very beginning, like initialization or in the enable?
I've never tried putting it on a transition. I'm not sure it would happen. It probably would be ignored because the transitions happen without any time interval. They're a point in space, so you'd be defining a variable for such a brief moment in time. I don't think the solver would care.
Well, how does it care about P and V then?
Because okay, let me think about how to say this. We're talking about continuous states, right? So it cares about P and V because that has some interval, some time. We're talking about a continuum of time. So if you tried to say P dot equals something on a transition, or V dot, you're breaking up the continuum and you're defining something that's no longer continuous. It's going to have like a real quick change. So we could try to define it, but
Constant though?
okay. I see what you're saying. So let me put this in. I'll show you how it works as it is. It's a good question. I hadn't thought about it. So 12. Yep.
And do semicolons generally matter, or does that freak out or have any weird output if you don't put the semicolons in?
It does depend a little bit on where you are, but most of the time you'll actually see the output to the command window, and it'll make the simulation run slower because it has to do that.
It'll still span the command window.
Yeah, so it's, yeah. All right, so I'll save this guy as all state. Okay. All right, now I wanted to do this because there's some things you have to know about to make this work right. So we have to go to the chart and make it continuously updated first, and we have zero crossing detection checked. And then within the chart, I have to go back and update the chart so that this stuff knows what I'm talking about. We don't want those. This is an output, and those are locals. So we'll say OK. All right. Now when I look in here, we have P and V. So by default, those are discrete, but I can change them to continuous. They're local variables. Oh, got to apply that. So I'm changing them to continuous, saying apply. So now, because they're continuous, then the underscore dot makes sense to the solver. And now when we look back at this and update the diagram, it's not going to complain and ask me, hey, what's this underscore dot business? Because it knows that that's implicitly the time derivative.
Oh, so that's actually a recognized thing to add on to a variable.
Yeah.
So like Tony underscore dot, it'll know that that's the derivative of Tony.
Exactly. You got it.
But Tony has no derivatives either.
That's right. I am the exponential.
We should know.
Yeah.
That was pretty nerdy there.
Yes, it was. That was pretty nerdy. Okay, so we have P out. Let's put a scope on it real quick. FF scope. So if I hit play, we should see something bouncing. And we do. Pretty cool. So you wanted to know if we made, what did you want to do? Like v dot something? V dot equals something?
V underscore dot equals -9.81.
Well, okay, I'll just put it in. It should work because it's not going to interfere with the continuity of the during state, because that's what it does here.
Yeah, because I figured it's always going to be that value. Well, if you were to omit it from the during state.
Yeah, okay, that's what I thought it would do. It says, in continuous time state flow charts, derivatives can only be assigned in during actions.
Okay, got it.
So it's illegal in that context.
Okay, so it's just the MATLAB rule thing.
Yeah, whole rule thing.
Damn rules. They're making me broken.
Okay, so we could do cool stuff here and make it actually lose energy. Remember, we had some energy issues before. Make it kind of damp out. But this is, I guess my point here is, this is so much more compact. Like the efficiency with which we expressed the exact same thing, there's literally like 10 lines, 12 lines, something like that. And some of those lines are brace. I mean, there's very little there. We just had to tell it what some of the things meant. So, as soon as you start doing like software models of state machines and try to code up the same thing that you made, like with like 6 states and a couple, 4 or 5 transitions, and you'll be like, Stateflow is the way to go. It doesn't take much at all, and it's just easier to do. So that's the bouncing ball.
So that's just because this is so easy to code up because Simulink understands the whole derivative thing and associates that.
Yeah.
Okay.
Yep. Okay, so we already did this. Went through P and V, made sure they're continuous. Okay, Simulink masks. So, okay, I'm going to talk about what this is, and then we'll use it in just a second, and that'll be easier to actually demonstrate. It'll take less time. Simulink masks are a way that we can explicitly say, I don't want to have to dig down in to change this in a subsystem or this in a block. I want to restate it in my own terms. And so they're a mask in the sense that they abstract us from the details of what's behind the mask. And so maybe you want to put in, maybe when you say you want to make a parameter like acceleration, and you want to define it in terms of feet per second, but you want your system to define it in terms of meters per second, you can put in, okay, the parameter is feet per second, and then put code behind it in the mask to convert that to something else. Just one way you could abstract. Or maybe you have 3 variables on the inside that are all derived from one parameter that you can put in. You don't want to change all 3 every time. So we're going to skip the tap delay because we'll do that next time, just in the interest of time. So, coastal defense system. Yeah.
Is this related to the movie?
What?
Is this related to the movie?
This is our big project over all the seminars.
Oh.
Yeah. So we're trying to finish the software stuff, and so architecturally, the problem we're going to solve, more just talk about, is what's left. And we've already talked about that a little bit. And then the 2 things we're actually going to get done today are the elevation and time of flight solution algorithm and the time horizon, like how far ahead we need to lead the ship in order to hit it. So here's what's left. We have to predict where the target will be in the future. So that's the prediction aspect, because it takes, we're shooting at something miles away. When you stop and think about what we're doing, we're shooting something faster than the speed of sound, 25, what's the speed of sound? 700 or so, right? Right, yeah, and we're shooting, right? STP, right? we're shooting at 2,500 feet per second. That's our muzzle velocity. So I don't know how many times, what Mach number that is, but it's faster. So around Mach 3. It's faster than sound. So our regime, like what we're trying to do, is not a real simple, easy thing. I was reading a bit about ballistics and trying to see if we could, make this more accurate. And what I found is it gets really complicated really quick in ballistics. And so we're not going to do much more than just have some air drag, which won't even be that accurate, but it'll be better than nothing. And we'll have our collision with the water, and that'll be it. But even so, it's not going to be an easy problem. So we need to predict where the target's going to be in the future. We've got to calculate the elevation because we need to aim the cannon, right? And we don't have all of those circuits and that three-dimensional geometry yet. But once we do, we need to point it at something in order to fire. So we know the radar will tell us how far away something is, but we still have to calculate, well, I know my muzzle velocity. What does that mean about what angle of elevation I need to shoot at? We also need to know the time of flight, because that's related to how far we have to lead the target, right? And obviously how far in advance we need to predict. And then, so that's the lead time. And then finally, we need to decide when and where to shoot. Someone's got to ultimately pull the trigger. In our case, the software is going to be going to have the little button, the red button. So the things we're going to do today are in the orange arrows. We're going to calculate the elevation and time of flight, and then we'll calculate the lead time for the shot. And we're going to put off the prediction and the decision control until next time. They are more complicated, and so I'm working on making them less complicated so that we can do it in a couple hours. But these two are pretty fun. So we're going to, and what I'm showing here with the arrows is kind of the flow of data. There's actually some other things too, like calculating the lead time for the shot kind of comes in between this arrow to figure out which prediction we're going to use to get our elevation. So some of this stuff is simultaneous, and you'll see what I mean as soon as we start doing it. But this is kind of on the high level. This lets you see, okay, the first thing we got to do is predict. We need to predict where they're going to be. And then we need to do this. And ultimately we have to decide whether we pull the trigger and when. So, okay. So the first thing, we want to be able to calculate elevation and time of flight. So if we stop and think about it, this is almost all done for us. Yeah, hopefully that doesn't go off. That might. Laptop and on. Okay, just making sure the projector doesn't go off. So we've already written the shell tracking algorithm. We did that last time. And if you stop and think about that, that's implicitly solving a solution, right? It tracked, Colin, you pointed out, hey, we need to know when this hit. So that was our time of flight. We know when we launched, we know when it hits. We know what the range is because we know what the X and Y positions are at that time. So all we have to do is kind of invert the problem and say, okay, what we actually want to do, we have range. We have the range we want. So what if we look at this as a control system? And I think this will be a good exercise for us to do because it's a different way of posing the problem. So we can look at this and say, try this. Oh, that didn't work. Let me get you going in the right direction. Try shooting here. And more often than not, that's the way we as humans think and learn anyway. So I think it's a super valuable thing to actually make a piece of software that does the same thing. Okay, so because of the fact that we're reposing this or reframing this as a controls question, I just wanted to show you very quickly what a proportional controller diagram looks like, because that's what we're going to be implementing. And it's pretty straightforward. You have some state that you want to be in. In our case, it's going to be some range that the radar told us, okay, the ship is at however many feet. And then we're trying to get the elevation angle to be that far away. So we can measure how far away in simulation our shell actually hit the water. And then we can change, our control signal is going to be our change in elevation. And we can modify that with a little gain, and that's the whole thing. It's very subtly complex. It's not a hard concept, but in practice, control systems are pretty complex. So this little KP here, we need to amplify the error signal so we get there fast enough. So here's some of the solutions of that. So if we make it too high, that KP is too high, it will oscillate. And basically the solution will never be able to settle down on where we should hold the gun level. So keep in mind, what we're doing here is we're controlling a solution. And anybody have taken controls? You've taken controls.
You said in about 2 to 3 minutes what Gindackley took about 3 classes to take, and he called us idiots many more times.
Oh.
So thank you.
Sure. Well, you're not idiots. And I am definitely glossing over a lot of details. So.
Oh no, he glossed over more.
Oh, okay.
He just managed to somehow fit it into many more words.
Okay.
I don't know. It was incredible.
Okay. Well, I won't comment. So what we're looking at here is there's 4 conditions basically that we could tune our parameter, our proportional control parameter to be. And if we tune it too high, it will become undamped. And this thing will hunt back and forth trying to find a solution to hit our target. If we do it too low, it'll be underdamped, and that's this purple, and it'll take too long. And then we'll be sitting there waiting so long to get a solution. By that time, we'll actually need to be aiming somewhere else. That's not going to help us. So we kind of want to be in the either overdamped or critically damped. I guess any of these 3 would be okay. Critically damped would get us to our solution as fast as possible. Overdamped just means we'll overshoot sorry, critically underdamped means we'll overshoot. Okay, I don't want to beat this one to death. But let's just think for a second about KP, being aware of what we're doing. We're converting. If we go back here, what we want is a particular range, right? And what we're controlling is a particular elevation. So what we're doing is converting a range to, in a sense, we're converting a range to an elevation angle. And so since the elevation angle is like 0 to 45, and the range is like more than 10,000 most of the time, just to get it in your head, like scale-wise, we're going to be less than 1. KP is going to be less than 1. If you start, you put 2 in there, the cannon is effectively doing this whenever it's trying to solve something. It's, oh, that's way too much. That's way too little. You have to get KP kind of in the right neighborhood. Okay, so we need to add a mask to this. Anybody ever seen V for Vendetta? Yeah. Say what?
Guy Fawkes. That's the name, Guy Fawkes.
Oh, right.
He does have a mask like that in Mr. Robot. That's an interesting show.
I've never seen that.
There's a lot of hacking in it, and the hacking actually is realistic from as per Ars Technica.
Okay.
So those guys are kind of being all about that sort of stuff. So
Okay.
they have this person who talks about that. A good show.
Okay, cool. Yeah, so we're going to modify this algorithm, and we have a MATLAB function block already from last time. And so here's what we need to make changes to. We're only going to track 1 shell. We're just going to launch it over and over and over and over and over so we can figure out what we need our elevation to be for a particular range, right? You have a question, Josh? Okay. We're also going to be telling the algorithm that it's operating at 2,500 hertz so that we can get within a foot. Remember, our muzzle velocity is 2,500 feet per second, so we're going to be operating at that time step. but we're going to run the algorithm faster than that because we don't want to wait 100 seconds to get one solution. So there's a little bit of mental gymnastics to wrap your mind around that, and you'll see what I mean in a little bit. And when we need to add a time of flight, and then we need to add a complete output so that the block on the outside knows, hey, I've splashed down. And then we need to be able to reset it so we can launch the thing again. So there's just a couple things to add. As I say that, there's like 6 things to add, but they're fast. So, let's see.
Gavin?
Yeah.
This is kind of going back a little bit, but when you're talking about the relationship between your angle and your range and how that relates to KP, you were saying that you wanted some kind of one, because the relationship between the two of those,
Yeah.
you didn't want to oscillate and go back.
Right,
back
right.
and forth. How, I guess, just when I was thinking about it, like, how does the relationship between the angle and the range relate to, what is KP, I guess? Like,
Yeah. So KP is just a constant.
okay.
It's something, it's a gain.
Okay.
So like this part right here, we're just amplifying an error signal. So let's say that we want the range to be 10,000 feet, okay? And let's say that we set our first elevation angle at 20 degrees. And we launch it, and it's actually 20,000 feet, okay? So then our desired state is 10,000. We measure 20,000. We form an error signal of 10,000 minus 20,000, so that becomes negative 10,000, and we multiply it by something. And then we change, or we control, what our elevation is. So if we made, so now the error signal is 10,000 of, in our case it's feet, but it's the number 10,000. So all I was trying to say was, we want it to be a lot less than 1, because if you multiply 10,000 by 1, you're trying to change your elevation angle by 10,000 degrees.
Gotcha. So you're pretty much, your KP, your constant in there, is pretty much defining for an X change in degrees of the cannon, this is going to be the change in range. Or
Right.
if we want to change the range, just not this, we change the cannon.
Yeah.
Gotcha.
Yeah. Okay, so, yeah.
Or we're also updating it through that Stateflow, right? Because it's guessing and readjusting, right?
Right, so it's going to iteratively guess.
And the KP is kind of the step that it can take.
Exactly.
And if you give it too many steps, it's going to take too long. But if you give it too big of a step, it's going to miss.
Yep. You got it. That's it. Okay, so let's do this. So I'm going to go back to day 5B and get our shell tracking model. So I'll copy that. Put it back here. Paste. Open it up. I'm going to close the other ones because they're just going to get in our way. Okay. Alrighty. Where'd you go? Okay. So we need to change some things. So first of all, we want to change, I'm going to maximize this thing so we've got some room. So I'm going to take out T and I'm going to put in reset. And I'm going to add position out. I already have position out, but I'm going to add complete to the things that we're going to output here. Okay, I'm going to change N to 1. Muzzle velocity still 2,500. All this stuff's good. All this stuff is good. I'm going to add a persistent variable called t that we'll be able to reset to get our time of flight. T equals 0, and so I just initialized it, and then during the time update, I'm going to say if velocity 1, I guess I need to say I1 is greater than 0, say 1, 1. It's greater than 0. T equals t plus ts. So we're just keeping track of time there. I think we'll come back to adding something about drag. For the moment, we'll just leave it as is for the sake of time. It's an easy thing to add, but I think it'll just make things more complex than they need to be. Okay, so for splashdown, we want, if it does splash down, we want complete to be equal to 1. Otherwise, we want complete to be equal to 0. And what else? I guess we need t out, time of flight, to be equal to t. Okay, and we need to add time of flight up here. All right, so let's save that. And let's just see if, oh, we need reset, don't we? All right. So change that to n, set it equal to n. Just because we're not doing 100 now, we're just doing one shot. So I'm just changing that a little bit. So if reset equals 1, then position 1 equals, oh, might as well just do this faster, right? Sheesh. Reset them all to 0. Our velocities will already be 0. I'll do that for that. Okay. So we can get out of there. Go back to the model. All right, so a couple things we need to think about changing here. Position out is a vector. That's fine though. We're only going to use one of them for our range because we don't really care about in x, y. We care about our total range. I don't want to do any extra math, so I'm going to give it a bearing of 0. So that means that the x is going to have all the range, and we can ignore the y. That way we don't have to do anything extra. I'm going to change the ts to 1 over 2500. Okay. So that's our time step. Now that's the time step that the model thinks it's solving the problem in. But that is not the time step we're actually going to be running the algorithm because we don't want to wait 100 seconds to get an answer. So, all right. I want to put in, I'm going to make the elevation a port, and I'm going to make the reset signal a port, and then complete, and all those things will be ports. So I'm going to highlight this whole thing and say, please make me a subsystem. Okay, so now that it has ports, this is elevation. This is reset. This is time of flight. This is to let them know we're complete. And this is our position. Okay, very good. Now, because I'd rather do this with masks for a reason you'll see in just a second, I'm going to right-click on this MATLAB function block, go to block parameters, and instead of saying, use something explicit, I'm just going to call it TS. And now, on this subsystem, I'm going to right-click and create a mask. And so with this, I'll click on the parameters dialog and add a little edit control and put in a sample time. And it'll be called TS, and we'll make its first value 1 over 500, how about? And say, okay. That's good. It turns white and makes this little arrow thing here. And I'm going to, and now when we double click on it, it just does this. So we've abstracted all those details. All we want to change is the sample time. So that's good. Let's see. That's probably enough. Okay. So let's just make sure this works. So let's put some constants in front of it. Oh, come on. For an elevation of, how about 20? And don't reset. I just want to make sure this does do what we think it's supposed to do. Put a scope on this. We'll have to put a demux also with 3 outputs because remember we were previously calculating a 3-dimensional thing, but now, man, what's the deal? There it goes. Okay, and we'll watch the complete signal, and we'll watch the time of flight signal. All right, so let's run this. Oh, already messed up. We need to change our sample time here to be 1 over 2500, and we want to go 100 times faster than normal. Did I put the other? Yeah, I did. Okay. So this should solve in approximately 1 or 2 seconds. So that way we don't have to wait so long. So hit 1. Hit go. And it looks kind of like it kept going. Let's watch the Z variable and see if this looks right. Oh, I have it for 10. I meant to put 10 seconds. That's why this is leaving us.
Yeah, I got it over to 8:30.
Oh, no problem. I'm just.
It's on the video, right?
Yeah.
I sent him the information.
Great. See you later.
When's the next one?
Same time, same channel.
Next week.
Yeah, Wednesday at 6:30.
Thank you.
Yep. Okay, so this is solving. It's going very slow though. I feel like we're not getting gravity to help us. Let's check out our. Let's go underneath this thing. Bearing is 0, elevation. We'll put in TS is 1 over 2500. Okay. Doing 1. Oh, fire 1. Yeah. We need. Okay, this should be a pulse. So let's just fix the fact that we've already fired. We will put in a MATLAB function here and just solve this little problem. Function y equals, what would you call that? You guys got to help me with the language. It is not a spike, it is a rising edge. So if, I guess we could do this with the state machine too, but I think this is faster. And we'll need a persistent last if is empty last equals 0. Okay, so if u equals 1 and last equals 0, y equals 1, else y equals 0, and so I'm just making sure that it is only on for one sample time. And then, once that has happened, last is equal to u. Okay. Save that. So this will just be in between our fire1 constant. That way it'll only fire once, and it'll actually let us do something. Oh, and we need to give it the same TS. TS. Okay, let's try that again. Much better. That looks more like a shot, right? That's a Z. Okay. So let's see if we were indeed complete in about that time. Yep, complete went true. And time of flight is 4,000 seconds. I don't think time of flight is updating, right? Let's solve that guy. You know, as much as I would like these things to go absolutely perfect, I think if you guys are watching, you'll learn more from the problems that we're solving, like the little problems. So let's solve the time of flight one real quick. T equals T plus TS. Oh, we need to reset T. T equals 0 on a reset. And time of flight equals T. Okay, so as long as we're traveling, we should be updating T. Okay. Boy, just stays there. Okay. Let's figure out why that's happening. Bearing 0. Just going to make sure I'm not looking at the wrong one. So I gave it a bearing of 1, so I'll have just a tiny little bit of, nope, that's not it. A tiny little bit of in another axis, but that wasn't the problem. So I'll go back to just 0 there. That's important. Gotta get that one figured out. I think I set reset to 0, didn't I? Yep. Okay. Do you have a thought? Oh, I just saw you stretching. Thought maybe you had a thought. All right. Oh, This should not be inside the fire one. That's why. It should be in the update. Oh, we'll put it right outside the update actually, because there. That's fine. Good. That should do it. So time of flight should come to. It should accumulate values, and then once it hits, it should stop. There we go. So that one took 53 seconds or so. That's what we wanted. Okay, very good. So now stuff is working like it should be. And you might notice that our z-axis, it took us about half a second to calculate each shot. So we're simulating a simulation, if that makes sense. We're accelerating the simulation to faster than real time. So it works for what we want it to do. All right, now we have something that works, and I'm going to get rid of all these guys. So just make it go slower. And we'll put in a chart over here to control this thing. And so this is where it's going to stop looking like control systems. If you guys have seen any control systems, this will look like a different kind of control system. So, but it actually is the only way to do this, or not the only, there's never only one, but it's the easiest way to do this because of the fact that we have to wait for it to finish for so long. So we're not operating on every sample. We're operating on, go take a look, I'll wait for you to be done, I'll come back when you're done, that kind of an idea. So we need an initialization state. And we'll say on entry, reset equals 1. And that'll be good. And then we need like a first try kind of a state, because we're going to use all the runs after the first one to calculate a new try, but we need like a starting point. So we'll call this the start point. Entry and elevation try will be, we'll just say it's 22 degrees. And let's see. We need to do a couple of things here. So fire 1 equals 1, and reset equals 0. I feel like I'm forgetting something though. Elevation or reset, okay. All right, so I'm going to update the diagram, Control D. Reset is an output, elevation try is an output, fire 1 is an output. Okay, that's all good. That's going to happen in one step, unconditionally. Okay, and then as soon as we've run the first one, now we can mod the elevation. So on entry, for most of the stuff you'll just put on entry, do something. It's kind of in special cases that you use the on entry and during and exit. So almost everything we'll just use entry. So we're going to form the error signal. I want to point you back to this real quickly. So the error signal is the place we want it to be subtracted from what we actually got. That's the error signal. So when we do this, we'll call it error equals what we want it to be, which we'll call range ref, minus what we actually got, which we'll call range out. Okay, and then lev try is going to be equal to whatever lev try was before, plus k, we'll just call it kp because that's what they usually call it, times error. So again, all I'm doing is implementing this in code. I created the error signal, and then I amplified by some input. And that's what's going to give us a new control. And so this will happen as soon as complete equals 1. So I'm going to update the diagram again. And we've got a bunch of new things. Range out should be an input, because that's coming from our simulation. Range reference should be an input also, because that's coming from what we want. KP is an input, because we're going to put that on a block outside. Complete is an input, and error is a local. It's all good. All right, and okay, now we need some place to kind of walk through doing the reset, fire one, all that stuff. So we'll first do a reset. And we'll do this unconditionally. No, it's not going to like call that the same thing. Reset equals 1. And I didn't put anything in, so it assumed I met entry, which is typically what you do. Okay, then I'm going to make another state here, and then I'm going to do fire state, fire 1 equals 1. So each of these are going to happen unconditionally. I just want them to happen in sequence. Then I'm going to let go the trig. Can't have any spaces in the name of your state. And so that state on entry, fire 1 equals 0. And then finally I just need a state to kind of hang out in until I'm done with the solution. So I'm just going to call this the wait state. Entry, there really isn't anything to do. So we just need to hang out for a little bit. I also need to turn, I just realized, I need to turn reset off. And that'll happen unconditionally, and this will only go back when complete equals 1. All right, so I'll pause here just a second, take a look at this. Does this make sense what we're doing? Yeah.
So the model that we have, it's going to be firing off shots, then reevaluating. It's not going to like guess and then shoot. It's just going to shoot and readjust and shoot and readjust, right?
Say that again. I didn't quite follow you. What's the difference between those two things?
Well, one fires a bullet, and then the other one waits until it finds a solution that feels will give it a margin of success, and then fires it. Does that make sense?
Okay, I think I follow what you mean. So let me connect these. I think it'll answer your question. They're doing it together. So if I connect fire 1 to, whoops, I need a fire 1. Oh, that was a big thing to be missing. Might need one of those. I think I follow what you're asking, and they have to work together on it. Or maybe you're asking if you could fire multiple things while you're guessing. So
I'm asking, does it make multiple guesses before it fires, or does it make one guess and fire?
One guess. Because the reason is because it needs to know, it needs the feedback of how far that went.
Right.
Yeah, sorry, I misunderstood you. Oh, and I didn't call it something I could understand. I need to call this fire 1. Okay. Okay, so connect up fire 1, the elevation we're going to try, and the reset. Oddly enough, they're completely opposite orders. That's kind of funny. And then I'm going to take just the x coordinate, and that's what's coming into range out. And and I'm going to give it a constant for our reference for the moment. Let's just say we're trying to hit something that's 12 miles out, so 12 times 5,280, I believe. Does that sound right? Okay, so here's our KP. Let's just try 1e minus 3 to start with. So 1/1000th. And then we also need to connect complete. Okay. So here's our system right now. And I'm going to do Control D, because it's going to whine at me about a few things. Yep. Okay. That didn't get finished. Save. Control D. Okay, so it can't solve the algebraic loops. And that's because of the fact that these two things are dependent on each other, you have to say how they can talk to each other at exactly the same time. That doesn't, right? It doesn't make mathematical sense or even software type of sense. So we just have to add a couple memory blocks in here to sort of break up the loop. And I want complete to inherit the sample time, and I want the initial condition of that memory block to be 0. And this is going to be pumping them in real fast, so I don't really care what the memory is there. That's fine. One other thing, I'm going to, because of initialization stuff, like the initial condition coming in, I want to make this after 1 sec. And that's going to look at simulation time. So that's just going to say, don't do anything for the first second of simulation, and then you can act normally. Because that way it'll give stuff to kind of initialize, give things a chance to initialize themselves. Alrighty, so we are now ready. So let's turn this thing on. It's kind of the cool thing and the bad thing about control systems is they don't work without being all connected as a system. You can't test this part or that part without, you know. To some extent you can, but as a system, to control something, you can't do it without. All right, so let's see how fast we can go here. Oh, I already forgot something else. We need to set how fast this one updates, right? Right now it's updating just as fast as the subsystem is, which is really fast. So it's going about 100 times faster than it needs to. So let's just make that 100. Because if you think about it, most of the time you're waiting. This is doing a whole bunch of stuff, and this one's just waiting for a solution and making a little adjustment, saying go do the hard work again, I'll wait for you. So I'll set this to 100. Save. Or 100 hertz is what I meant. All right, let's try this. So it should do nothing for 1 second. Or maybe it'll do nothing all the time. Huh. All right. Did we ever pull the trigger? Let's check on that. There's no signal. And we're stuck at. Oh, that's weird. Okay. Fire 1. Oh. Okay. We just need to turn it off. We left fire 1 on. Fire 1. That will be on exit. Fire 1 equals 0. Yeah, that should. Okay, I'm going to initialize it to 0 too. because we have that block in there now that's checking to make sure it's a rising edge. So we need to make sure that it's 0. Alrighty. And it still does nothing. That's really weird. You see down here it's got time running, and here it doesn't look like it has time running. Fire 1. Man, tonight is not my night. And it's going to be immortalized on YouTube forever. Darn. Okay. All right. Let's think about this. Fire 1 is a signal. It is connected to fire 1. Elevation try is connected to elevation. Reset's connected to reset. This we know. Okay. We do initialize this stuff. Let's watch this. Watch it go through the states and see if it's going where we think it should be going. And well, that's really disappointing. It is not. So I'm going to get rid of this thing. For some reason, it's not wanting to transition. So. Boy, that's bizarre. Maybe it wasn't actually connected. Okay. So you see what I'm working on here? It's an odd situation. I'm not quite sure what's going on. On entry, we do these things. We have an unconditional transition to go to starting point, where we do some stuff. For some odd reason. All right, let's hop in the Model Explorer and see if we can figure this out. Filter out. I'd kind of like to see the transitions and make sure they're connected where I think they're connected. Source. Init to start point. They are connected. Unconditional. I am updating this thing at a certain rate. Oh, it's 100 seconds. Sheesh. We're waiting 100 seconds for our first update. I wonder. All right. Let's put this back the way it was. Sorry about that, guys. After, I'll just say 0.1 sec. That's interesting. It is solving a whole bunch of times. But I think our constant's still too big, our KP value. So I'm going to put this over here. And I don't know if you guys have seen this yet, but you're going to like it. So we can make our solve time infinite, our end time, and just let it run and change parameters. So I'll pull this back so we can see what's going on. So we can dynamically change these values, and this is something you can't do in MATLAB, right? Because the script is locked when it's running. So I'm going to change it to 1e minus 4. So that's going to change the update rate try 1e minus 5. We're still kind of bouncing around. It is looking like it's converging, huh? Let's see, so 12 times 5, about 5,000 is around 6,000 something, which looks like it's actually converging. That's good. That's good. So it's just kind of slow in its convergence. I think we can crank it up a little bit. So I'm going to make it 3. I think it'll still be stable there. And I also want to make another. I'll just have a sum here. Sum. So that you can actually see the error is being driven to 0, because that's kind of the critical part here. So we are pulling in range out. That's basically the error signal. Let's take a scope and look at that. So we don't do anything for the first however many. So the error happens to be negative, but we're driving it closer to 0 on each step. Follow what we're doing there? That's pretty cool. So this is actually coming to, as soon as this gets within a certain range, then that will put us at 0 error, and that will mean whatever elevation we're using is what we should use to aim the gun. So, and this should be error. Why is that oh, it is 0. Yeah, the final value is 0. I was looking at, we're outputting the range the whole time, so during the simulation it's also showing us this stuff. So we're really just talking about this bottom point here. In fact, just because that's hard to look at, let's go to the Model Explorer and make this, come on. I'll catch you there. Yeah, we'll just make this chart. The error will now be an output as well as a local. So that way we can plot this a little easier. A little easier to see what's going on with the system. So again, the system's just trying to drive the error in the solution to 0. And if we had, apparently 22 was too high or too low, maybe too low. So we had to pull up a little bit, and here it converges. And we can set our parameter of basically how many feet, how many feet is good enough. And in the beginning, remember, Vasily was like, well, I've got a solution, it's a little rough. This is where we decide how rough is okay. Is 5 feet okay? Is 2 feet okay? And we're trying to hit a particular size destroyer. How accurate do you need to be? Maybe 3 feet's fine. So I think that's a good place to stop. You guys have any questions before we call it? No. I think this is a pretty cool thing because what we just made was a solver, really, a specific solver for our problem, and we can go change the model of we could add air drag, we could add all kinds of other cool curvature of the Earth. Ron wanted to add the other day. We could put all that in there. The solver will still work so we don't have to go back. I'm sure it'd be more computationally efficient if we explicitly solved for, I have this range I want, what's my elevation? Like we could go spend a bunch of time doing that. But the interesting thing that we traded here was we didn't explicitly solve it, we implicitly solved it. So now, when we add more conditions to make it more accurate, we still have a solution. And that's pretty cool. So hope this has kind of like expanded your thought about what a control system could be, because a lot of people don't think about the fact that you really can't control anything you want. So anyway, that's it. Thanks.